question 2.4 is a problem that involves a sort of a rocket launcher, essentially, a launcher of fireworks, and so that's the package of fireworks, and you've got a big spring, and then it gets fired down the barrel, and then the question asks what is the speed of the package of fireworks once it leaves the barrel, and we're going to use energy methods to work that out. It tells us that the packages have a weight of 44.5 newtons, so just to start with, let's write down what the mass of the packages are. So that's 44.5 divided by 9.81. 44.5 over 9.81 is 4.5362, which is good, 4 significant figures, 4.536 kilograms. And let's draw a little pretty picture. So that's the package there of fireworks. There's the spring, which is initially sort of compressed, and then it's going to fire off. So let's call that position 1. And once it leaves the barrel, so when the package is in that position, we'll call that position 2. And this is at some angle 60 degrees to the horizontal. Right, the only forces that are acting on the package of fireworks are the spring force and gravitational force. So, and they're both conservative forces. So from our lecture, we know that if a system has conservative forces only, then we can use the fact that the potential energy plus the kinetic energy is constant. So in this case, we can write V1 plus T1 is equal to V2 plus T2, where V is the potential energy and T is the kinetic energy. So what we eventually want to find out is what the kinetic energy is at position 2, but we'll start by evaluating these other terms one by one. So let's start by working out what the potential energy is at the initial position, and we can define a datum such that the potential energy of the mass of the fireworks is 0 to begin with, and the only potential energy then at position 1 is the potential energy stored in the spring. And we have an expression here for the potential energy for a spring, which is half Ks, and I'll use the subscript 1 to denote that we're interested in the stretch at position 1. Now stretch is was defined in the lectures, here it is, define stretch as the difference between the length of the spring and the unstretched length of the spring. So the unstretched length of the spring in this case, it states it in the question, is the length of the barrel, so 762 millimeters. So that means that the spring is compressed. So if I write down the expression for stretch, so S1 is equal to the length of the spring at 1 minus the unstretched length, which is 7.762. So initially the length of the spring is 0.1524 minus 0.762 gives us our initial stretch. Just work that out. That's 0.1524 minus 0.762. So it's minus 0.6096. So this distance here, by the way, then has got to be equal to the same, 0.6096. Okay, so that's fair enough, and we can now just put that into there to work out what the potential energy is. So half times K, which is 1,300, times, so half times 1,300 times the stretch minus 0.6096 squared. Now the negative sign doesn't matter because we're squaring it. 0.6096 squared gives us 241.5 Newton meters. So that's the potential energy initially that's stored in the spring. The initial kinetic energy is simple enough because it's at rest. It says as much, and that sort of makes sense because it's a launcher. So the initial kinetic energy is 0. Moving on to the potential energy when the package has left the barrel. Well, now the spring is unstretched because the unstretched length of the spring is the barrel length. So that means that there's no potential energy stored in the spring anymore, but there is potential energy in the fact that we've raised the mass this distance. So it was down here and now it's moved up here. So that H is what we want to determine, and we know this, sorry I haven't drawn this particularly well, but we know this length here is 0.6096, and because that's the length it's travelled along the barrel, and so we can work out the elevation with some simple trigonometry. So the elevation is 0.6096 times by cos 30, and cos 30 is root 3 over 2. So the elevation, I'll just do that now, 0.6096 times square root 3 over 2 is equal to 527.9 millimeters. Right, so now we can work out what the potential energy is. We know the mass, 4.536 times 9.81. Add in our elevation, 0.5279, and that gives us 23.49 Newton meters. So we've got 1, 2, 3, and now we can evaluate the kinetic energy. The kinetic energy when the package leaves the barrel is equal to half mv2 squared, and it's the speed that we want to find out, and that is equal to v1 plus t1 minus v2, which when we make the substitutions, 241.5 plus 0 minus 23.49 is equal to half mv squared. So a little bit of rearrangement. So let me evaluate the right hand side. Minus 23.49, that's the right hand side. We can take the 2 over and then divide by the mass, which is 4.536, and that gives you v squared. So I rearranged for v squared there, and so the square root of that answer gives us our speed, which is 9.8 meters per second. Okay.